ion collisions allow us to recreate the conditions from just after the Big Bang in the laboratory and to study the properties of what we call the quark-gluon plasma. So normally quarks and gluons are bound into protons and neutrons in the atomic nucleus. But when you collide heavy nuclei, you get very many quarks and gluons, a very high density, high temperature, 10 to the 12 Kelvin. So this is more than 200,000 times the temperature of the sun. And in that case, the quarks and gluons are what we call deconfined. They can move freely throughout a larger volume in the colliding system. So in a kind of little bang nuclear soup that we make in our collisions. We take collisions the whole year, and most of the year actually we get proton-proton collisions, and those are very important as a reference. We can study the same strong interaction between quarks and gluons in a more precise way using proton-proton collisions, where these high temperature effects are not present, and then by comparing the heavy ion collisions to the proton-proton collisions, we learn about what changes, how the interactions with this plasma change what happens in the collision. And we also find that in proton-proton collisions, where there are many particles produced, which we call high multiplicity collisions, there's a large density, and we see effects that look very similar to the quark-gluon plasma effects that we see in lead-lead collisions. And so what we study is how you go from very simple systems, proton collisions with few particles, via proton collisions with many particles, to the large colliding system with the quark-gluon plasma in heavy ion collisions.